stop my video. Okay. You are recording. Okay. I'll stop my video just to. Okay. Here is the program. We are going to make a small introduction of what we are doing in JPEG, following by the presentation from Giuseppe Valenzi from the University Paris-Saclay, CNRS, Central Supélec. Is that correct, Giuseppe?
Yeah, perfect.
Okay, thank you. And his talk will be on learning-based lossy and lossless compression of light field. And minimize this. Then followed by Soren Forshammer from DTU Electrotechnical University of Denmark. His talk will be deep decoding of light field images. And Qingjing from Shenzhen International Graduate School from Tsinghua University on learning Planatic image compression with spatial angular decorrelation. And then we follow all the presentations by questions and discussions. Sorry. We highlighted the JPEG Pleno standard and learning-based light field coding activity. The JPEG Pleno standard, sorry about that, is comprised up to this point to 5 parts. Okay, the first part is the framework, part 1. It supports capture, representation, and exchange of planatic imaging modalities, such as point clouds, light fields, and holography. So far, we have only light fields as standards. We have a GPL file format, is a box structured file format. So it supports data, metadata, manipulation, editing, and so on. So we have space to point clouds for holography and light fields. We have JPEG Pleno Part 2. It's light field coding. We have 2 modes. We have 2 decoding modes, sorry. The 4D prediction mode that exploits the interview redundancy of the light field through depth-based warping. And we have the other one, which is the 4D transform mode. It uses 4D block partitioning, 4D DCT, and 4D bit plane exit 3 decoding. And we also have, sorry, no, sorry about that. And we have also the amendment, which are our profiles and levels. We have 2 profiles, the baseline block-based profile that defines decoding tools belonging to the 4D transform mode, and the baseline view-based profile that defines the coding tools for the 4D prediction mode. Okay, and of course we have JPEG Pleno Part 3, which is the performance testing procedures and test code streams, as well as the reference software, which is Part 4. All of them are already international ISO ISC standards. Okay. We started this learning-based light field coding activity. We started an exploration study on learning-based light field coding solutions, and we identified the main learning-based coding related domains, including light field compression, light field depth estimation, light field spatial super resolution, light field angular super resolution, mainly view synthesis, spatial angular super resolution reconstruction. And for what concerns light field compression, we have identified that most of the proposed solutions make a partition of the light field sub-aperture images into key sub-aperture images and no key sub-aperture images. And we believe that training material definition will be one among many challenges we have on learning based activity. And we believe that an efficient light field compression method needs to characterize the relationship among the number of viewpoints as well as the spatial correlation with the views. And so we started this learning-based coding activity within the JPEG, and we are trying to create the learning-based coding standard for light field. So that's why we proposed this workshop and invited 3 researchers that are working on this field. So thank you very much. If you would like to subscribe to JPEG Plano Light Field Reflector, please visit the light field registration, the list registration, sorry. And if you gather JPEG Plano information and documentation at our website. And you also can contact Peter, me, or Said, okay? And we can, oops, sorry about that. What's happened here? Just disappeared. My screen disappeared. Oh, sorry. So we have the program here. And we start with Giuseppe Valenzi from Université Paris-Saclay, Centrale Supélec. Bienvenue, Giuseppe.
Merci. Thank you. I'm actually Italian, not the original, but yeah, it's a long time I've been in France.
Grazie per
la... Speak all languages.
Sì, mio padre è italiano. Sì, grazie.
Okay, so I can share my display. Yeah. Let me do it.
I'll mute my microphone.
Okay. Okay, so you can see my display, right?
Yes, we can. Thank you.
Okay, so I'm Giuseppe Valenzi from CNRS in France. So I work in a lab that is the Laboratory of Signaling Systems in the University Paris-Saclay. So today I'm going to talk about lossy and lossless compression of light fields. So some work we did in the past few years. So just maybe some preliminaries, although I think that most people here are familiar with light fields, just for those that maybe are more new to the domain, maybe it's good to just introduce the basics. And I think that the basic concept is the Planatic function, which is a 7-dimensional function that describes essentially the light that you can see in any position in space from any direction at any wavelength and during time. So this is kind of theoretical concept because there is, you know, this of course entails a lot of information to be acquired, stored, and transmitted. So what people have done is to consider some approximation, some simplified version of this Planatic function. In particular, you can drop the time dimension, consider static light fields. You can consider only the wavelengths that are important for the human visual system. And then what you can do is also to consider that the light is constant along array, which basically give you the possibility to reduce one variable here as well, coming up to a 4-dimensional function, which is typically called the light field. And the typical way to represent this, it's what is called the true planes parameterization, in which you have essentially true spatial variable and true angular variable to represent your light field. And so why this has become popular, because it enables you to make some funny operation after acquisition, like changing the viewpoint of your scene, and also to refocus dynamically. And so the goal here of this talk and the work we did was when we started doing this, I think now a bit more than 3 years ago, was PhD thesis of Milan Stepanov. The goal was to say, okay, how can we use learning, and in particular deep learning, to improve the coding of light field? And so this means, depending on what's the task you want to do, it can actually mean different things. For example, if you consider lossy coding, there, the tools that basically you need to improve are transform and prediction. If you consider lossless coding, you already have tools like arithmetic coding, which are kind of optimal, but they are, to be optimal, they require to know exactly or very precisely the probability distribution of your symbols. So how can we learn these probability distributions? And in general, how can we use the geometric structure of the light field to improve the coding? And finally, how can we do this in an end-to-end way, which basically, gives you the possibility to learn all the components at once. So we tried to analyze these problems, and so we will see now what we propose for lossy coding of light fields. So this was a paper that we published at ICIP 2020. And here the starting point was the observation that at that time there was a boom of the methods for end-to-end learning coding of images, of 2D images. And the goal was to say, okay, can we use this kind of approaches also for 4D light field? How can we do that for light field?
Donc, du coup,
there is somebody speaking. Okay, so okay, so and the next observation we had was that, and this was known as well at the time, is that when you consider these methods, the learning-based approach that were available, they tend to have very good performance at low bit rates, but when you want to increase the quality, they had some limitations. So the other question we asked ourselves was, how can we improve the performance for high bit rates? So the background here that it's on which this work is based is a popular work for learning-based image compression. It's the work by Ballet and others, which is based on a variational autoencoder to code the images. So basically, the variational autoencoder is what, in signal processing, what we would call a transform coding here. So essentially, you have an input signal, you have an analysis transform, you compute latent variables, and then you reconstruct a signal, in the pixel domain using a synthesis transform. So the difference with the classical transform coding used in signal processing is that here, first thing, you have nonlinearities in the neural network, which make this more expressive. And then with respect to a typical autoencoder, in the case of compression, you need to add quantization and entropy coding. So there have been tons of work to study how to include quantization, which is not differentiable, and so on. The work by Ballet consider what is called a hyperprior model to estimate the probabilities of the latent symbols. So essentially, the hyperprior is a sort of side information computed through another autoencoder, basically, which is transmitted as well to the decoder. So we start by considering this kind of approach, which was which has been shown to be very successful for 2D images. And so the basic thing we tried was to say, okay, how can we apply this to light fields? So basically, we tried several architectures to code light fields, and the one that actually turned out to be the most effective was actually the simplest one, if you want, where essentially what we did was to stack all the subaperture images. So we consider the light field like a multi-view image, and we stack all the different views as as the color channels in an image. So you have as many channels as the number of views, and then we did we used basically classical 2D convolution to code the light field, and by minimizing array distortion loss. Now, if you apply this, this works, as I said, very well when you have very low bit rate, because the representations that you can learn are very effective and are much more powerful than simple transforms like DCT and so on. So at low bit rates, you see that the learning-based codec performs very well. But then when you increase the bit rate, you give enough bit rate to code the light field, the performance saturates. And in general, you get worse results than a traditional codec. So this was a problem that we observed. And the reason is that essentially, an autoencoder is intrinsically lossy. It's not done to make perfect reconstruction. So the question was, how can we operate on the full quality range? And so what we proposed was a hybrid scheme. So the hybrid scheme we proposed is a scalable codec, essentially. So you have a base layer, which is the learning-based one that I just described with analysis, synthesis, and entropy model. But once we compute this base layer reconstruction, we subtract it to the original, and we code the residual using a traditional codec, which could be, for example, HEVC, but you can use whatever codec you want. And at the decoder side, we do the opposite operation. So we reconstruct the residual and we sum to the reconstructed baseline. So for coding the enhancement layer, as I said, we use a codec, in this case, HEVC, but it could be we tried also scalar quantization, it works fine. We could also use LCVC, for example. Any codec would be good. I mean, it's quite independent from the base layer, and so basically we stack the residuals in a pseudo video sequence. So basically we you have a scanning order for the views, and then you put them as a video sequence, and you input it to the video codec. And so we did, we tried how this works on using the JPEG Pleno test conditions. So our work focused on lancelet content. So all the things I'm presenting now is about lancelets. And these are the results. So here you see the green and the blue lines are HEVC and one of the profile of JPEG Pleno. So the mule is the one based on 4D transform that is more effective for lancelet data. And so the red curve is our base line. And so we see in cyan here we have the proposed method, the hybrid approach, and you see that this gives you better performance on the wide range of bit rates. And this was confirmed on all the test set. So the gains are quite impressive. So to conclude this first part, what we try to understand here is how we can apply a learning-based approach for light field coding. And we saw that it is possible to design a hybrid scheme that is using at the same time end-to-end optimization for the base layer and a conventional codec for the enhancement layer. And so at the same time, we can learn compact representation for low bitrate coding, but also overcome the saturation problem with high bitrate. So the natural next step here would be to optimize both the base layer and enhancement layer in a hand-to-hand fashion. Okay, so this probably would give you even further gains. For what concerns the second part of this presentation, the lossless coding. So this is a work we presented in the last MMSP. Here the starting point is the great success that deep generative models have had for image generation, but also for image coding. And in particular, due to the fact that these models can estimate efficiently the distribution of image pixels. And so the idea was, how can we use these generative models to estimate context probabilities for light fields to do context-based arithmetic coding? And in particular, how can we leverage the light field geometry for the context modeling? And so the method that we proposed is the following: is composed by several modules. So we have view synthesis module to predict views. So here the idea is that you have, you mentioned maybe before, the key views, and so you have some key views, the sort of intro views, if you want, that can be coded independently, but other views can be predicted through the view synthesis. Okay, so the view synthesis here that we used, it's a learning-based one that was state of the art when we did this work. And so basically what you have here is a set of sparse set of reference views, and you can estimate an intermediate view using view synthesis. Once you estimate this view, you can use this as a predictor of the actual view, and you can compute the residuals. So here, what we do is to compute residual views. And to do this, we need an entropy model. So essentially, we need to compute the probability distribution, actually the conditional probability of a residual based, when you know the synthesized view. So this complex probability distribution is estimated through a neural network. So in addition to this, we also consider some improvements, in particular the sequential decoding, which is obtained by hierarchical view synthesis, and in particular by considering spatial dependencies, and we will see how to do this using autoregressive models. So basically, we propose two entropy models. Baseline model, which is based on a work by Menzer and others, that basically compute the residual pixel all at once. So you have your predicted view from view synthesis, and you estimate all the pixels of the residual view in a single shot. And then you model the probability distribution of the residual pixel as a mixture of logistic distributions. So this essentially it's gives you a parametric model, which turns out to be efficient to compute. And then you can condition the color channel. So you can do this per color channel independently, but it turns out to be more efficient if you condition each color channels on the previously decoded ones. So this is called an autoregressive model, because essentially you start with, you compute, for example, the red color channel for the residual, knowing the synthesized view. And for the green, you will use the synthesized view, but also the decoded red component of the residual to decode the green. And then for the blue, you can use the red and the green, and of course the synthesized view. Okay, so this is what is called an autoregressive model. So this is our baseline. So again, baseline here for us is if you want, we decode all the pixels of the residual view in parallel. But we can do even more. We can group. We propose another model that is based on grouping, which essentially consists in decoding only a part, subgroup of the pixels of the residual. And once you decode this group of pixels, you can go to a next group of pixels. So here denoted by 2. So the pixel in the group 2 are decoded using also the knowledge of the pixels from group 1, which is already decoded. And so on. You can find the third group here that is decoded based on group 1 and 2, and so on. So this is, again, an autoregressive model that is on top of the baseline entropy model. I skipped these details about the training, and I want to go to the results. So these are, so first thing, we consider different view orders, view ordering for the decoding. Okay, it turns out that it's actually quite important, the order that you use to make the view synthesis and then the entropy decoding. So we consider a single decoding in which essentially you have some reference views and you interpolate all the other views with the view synthesis. Or we can use a hierarchical model in which you do this progressively. So you start from, so for example, here on the right, you have 3 possible configurations. You start with the corner views here, which are denoted by 0. So the first one, then you have the views denoted by 1. Then once you have this, you use this to synthesize the view denoted by 2, and so on. So basically, you can imagine that doing this progressively can bring some advantage, because you can, you can basically correct your estimation on the fly. And in fact, this tend to give the lowest bit per pixels. So all of these are the bit rates that we attain. And so we compared this best model that I just showed you with general lossless schemes and light field specific lossless schemes that have been proposed in the literature. And so you can see here, these are the average results on the JPEG test condition that we used here. And we see that we can get some significant gain, especially with respect to the general lossless schemes that have been that you can use, like HEVC or FLIF or JPEG XL. The answers to the question we asked at the beginning here. So is it possible to use learning methods for entropy coding? The answer was yes. We saw that we can get some significant gains. And this is obtained by a mix of tools. It's not just a single tool, it's the fact to use view synthesis to exploit the geometric dependencies, autoregressive modeling, grouping, and so on. Probably one possible direction for improving is jointly training view synthesis and entropy modeling. I'm a bit out of time. I go quick here to conclude. So what's next? This were the works we did in this with this PhD student mainly. Next, definitely it would be interesting to consider also video, so to add the temporal dimension. There are not many works doing this, even for 2D learning-based methods. There are less work from videos than for images, of course. And another obvious things to consider would be the perceptual optimization that so far has not really been included. And so all the losses that we consider were essentially mean-square error based. And in my opinion, one interesting dimension that is growing a lot, and you can see in conferences in computer vision nowadays, is what is called the neuroradiance fields, the NERFs. There have been a lot of papers recently on this. So the idea here is that you have a 5-dimensional volumetric rendering. So we go one step farther than light fields. And essentially, you learn this 5-dimensional function through a neural network, right? And so coding NERFs, I think it's an interesting direction for to pursue in the future. Okay, let me conclude. I want to thank my collaborators, and of course Milan, who did most of the work, with Umer, that is a student of Soren, and Frederic as well, of course. And our funding, that was the Real Vision project. And I don't know if there is time for questions, but I'm open to answer. Thanks.
Thank you very much, Giuseppe. Grazie mille. I was so happy, and I forgot to introduce you properly. Giuseppe Valenzi is a CNRS researcher at University Paris-Saclay. He's the head of the multimedia and networking team. Giuseppe completed a master's degree and a PhD in information technology at the Politecnico di Milano in Italy in 2007-2011, respectively. In 2012, he joined the French Centre National de la Recherche Scientifique as a permanent researcher, first at the Laboratoire Traitement et Communication de l'Information, Télécom Paris Tech, And from 2016 at L2S, he got the French habilitation de recherche from Université Paris-Sud in 2009. His research interests span different fields of image and video processing, including traditional learning-based image and video compression, light fields and point cloud coding, image video quality assessment, high dynamic range image and applications of machine learning to image and video analysis. He is co-author of more than 100 research publications and of several award-winning papers. He is the recipient of the Eurozip Early Career Award in 2018. He served as associate editor for IEEE Transactions on Sequence Systems for Video Technology, Transactions on Image Processing, Elsevier Signal Processing, Image Communication, and he is an elected member of the MMSP and IVMSP technical committees of the IEEE Signals Process Society for the term of 2018 and 2023. And also a member of the Technical Audit Committee of Visual Information Process of Eurozip. Sorry about that, but visually, Giuseppe.
Very complete. Yeah, thank you. So you want to take question now, or
I believe it will be better at the end if you don't mind. Or
yeah, sure.
It's okay.
Yeah, perfect.
Okay, thank you. Said is going to introduce Soren.
Yeah. Okay, so let me introduce our second speaker, Soren Forshammer. He received his master's degree and PhD from the Technical University of Denmark, and currently he's a professor with DTU Electro Department of Electrical and Photonics Engineering, Technical University of Denmark, where he has been since 1988. He is head of the Coding and Visual Communication Group at DTU Electro, and he has been active in also following ISO IEC image coding activities since early 19s, contributing, for example, to JPEG2. He is currently coordinator of the EU MSCA ITN Real Vision. His research interests include source coding, image and video coding, processing of image and video, processing of image displays, quality of coded multimedia data, multi-camera light field image and videos, and also coding for optical communication and visual communication. The floor is yours, Soren.
Okay, thank you. Let me just see. Okay, thank you. I'll present some work on decoding of light field images. The architecture is general, but we sort of designed it and definitely trained it for a specific setup for decoding images. I'm, as said, Soren Forshammer, and this is joint work with Umair Mukati, who did his PhD within the Real Vision ITN at the Technical University of Denmark. So for the outline, as I said, we're gonna show results for a specific setup, namely for near lossless coding of light field images using epipolar plane images. And the light fields, to follow up what Giuseppe said, it's the same kind. We'll focus on lenslet, and for the geometry, the 4D setting given by, you could say, 2 image planes. Then I'll say something very briefly general about soft decoding of near lossless coded light field images, and then specifically present our work on deep decoding, or you could also say post-processing or reconstruction of coded light field images. And I also believe the architecture could definitely be used for the task in the light field applications than just improving the decoding. And then at the end, I'll present some results. Just very briefly for the lossless, near lossless coding, I'm not going to go into detail, but to sort of set the stage and what where our coded data comes from, and also introduce the API, which we'll use later. But very briefly, we're in this work, or on the coding side, we're aiming at high fidelity, high quality, so obviously by lossless, but also near lossless as we know it. We wanted something which was fast, so for that we started from the Calic codec, which is fairly fast. And then sort of the new element here is to use these EPI structures, the clear structures we see here at the bottom, and try to utilize them for better compression, and doing so by modification of different blocks of Calic. And of course, the EPIs is sort of a different representation of or imaging of the 4D light fields. Maybe more common are the micro images and sub-aperture images. Okay, but just briefly for the coding, as said, we would start out with Calic as reflected in the block diagram. I'll not go into detail, but basically what we did was to try to utilize the structures in the typical plane images. We have one example here, and sort of part of the structures are sort of these lines reflecting depths in the image scene. And then we modified Calic by including these EPIs a number of places, the linear predictor, capturing the lines. Then we have both the horizontal and vertical EPIs. We sort of combine the two for improved energy-based modeling, and also for better texture context. And all in all, we could improve performance with a, let's say, fairly low complexity compared to a number of the other schemes we see for light field images. So if we compare with some of the state of the art, we can see that we don't, in terms of bitrate, meet or match the MMRP, which is also a very complex scheme, taking long compression time. But with a sort of what we could call a reasonable compression time, we do get good results and better results than, say, the HEVC we compare with an CMS. But now going to sort of what's will be the core of the talk, the near lossless coding and improving on this. So we start from the very classic block diagram of just having a uniform quantizer in a predictive coding scheme, and with the uniform quantizer, scalar quantizer here on the differences, we can, at the decoder side, reconstructing at the center point, know that the differences will not be more than delta, where the width of the uniform quantizer, the step size of the uniform quantizer is 2 delta plus 1. So just very briefly for results. Now we could start with this so-called epic I talked about before, lossless, and just extended this with near lossless. And of course, we can decrease bitrate. Now going to lossy, of course, we don't have lossless anymore. We do have high PSNR here, but also we see as we increase the interval size, there's a clear drop in PSNR. And to the right, the distortion by construction is bounded by this delta, which defines the interval. So we here both have a control of the peak error or the maximum error, the inf norm error, as well as measuring the PSNR reflecting the second norm. Okay, so what could be the problems here, or what could be improved? So the uniform quantizer doesn't really exploit light field model. So it's sort of a fairly simple agnostic technique. And due to this quantizer and definitely going to larger quantization step sizes, we degrade the PSNR performance. So to alleviate this or address this, what we will try to do is to attenuate the errors in the reconstructed light field using a light field model. So we call this soft decompression. So it is here as seen a post-processor is done here. One could also envision the techniques we present included directly in the coding blocks, but here we do it as a post-processing. So so we sort of have the fairly simple encoder. The first decoder step here is also simple, and then we can sort of have a flexible component here that, if allowed or desired, we can add some extra complexity to improve the performance of the whole coding scheme. Okay. Of course, it's natural to consider learning-based methods here. So for conventional near lossless image coding, Sang and Wu presented a CNN-based refinement of image data. And now we sort of starting from here in our EPIC coder, we joined forces and addressed coding light field, making it designing the soft decompressor, the learning-based reconstruction for light field data. But we would still like to have a control of complexity, so not keeping complexity sort of within reasonable bounds. Of course, I mean, if you take the full 4D data set and try to capture the correlations here, then it would require a lot of computation and memory. So instead, we took an approach of considering the different or 4 different image representations of this data, where, as we had already from the encoder, the EPI are selected and supplementing the more direct or conventional subaperture images and micro images. And this is illustrated here to the right. I think I should say, I mean, where we're going and the decoding we're doing for light field, it's not tied up on the specific encoder we have here. We could, I think, apply this as done for any near lossless coding of the light field images, and also, as said, it could also be used for other processing of light field images. Okay, so what we want to do here is to exploit the 2D characteristics individually, and then thereafter sort of locally adapt to combine the 4. So sort of break down the problem to keep complexity within reasonable bounds and then try to combine. And for this, we chose and designed a network approach with the CNN designed for each of the 4 image representation. There's AI, each of the 2 EPIs, and the micro images. And then based on this, we do a reconstruction, and then we have another network, GateNet, deciding on the weighted sum. And then we sum it up, and then because we have this near lossless property with bounded errors, it can also be expressed as saying that we have a convex set. Then we can use a truncation, which is similar to if you would see it as a convex set that you project onto. And then we reconstruct. So I mean, this presentation is sort of high level, but now we can see look more into what can each of these representation contribute, and also see then how they actually do contribute in the train scheme. So the micro images, they're good when the region is flat. The EPIs that have the clear structure we saw, we have them both horizontally and vertically, but they are challenged by occlusions, reflections, and etc. And then we have the images, which have image properties, but also you can say in some sense are somewhat sparse. But let's see what the GateNet decided and how it used this. Of course, I mean, we trained, as I said, we trained on near losslessly coded images with EPIC codec. I think it's probably going to be basically more or less the same story if applied to other near lossless versions of coding. But of course, I mean, it could make sense to at least train and test if a given near lossless coder is applied. But what we see here, we can start with the EPIs, is that there is sort of the clear directional characteristic with the horizontal EPI picking up horizontally and the vertical picking up vertically. What we see is the weight assigned where light values are high values. So we find these high values at the edges here. We also see the micro images picking up, but sort of maybe in a more sort of noisy structure. And then maybe interestingly, actually, the GateNet doesn't utilize the reconstruction from the sub-aperture images much. So, I mean, this could maybe also be something to think about going forward with coding of light field images, this type of light field images. They're sort of the same class, the lens-led images, and I think also largely the same test images as Giuseppe was talking about. Okay, if we now look at the performance measures again, the rate doesn't change because it's only decoder we're changing. We can see the green and yellow are the soft decoded, reconstructed using the network, and we see that they increase relative to the just the straightforward decoding out of the near lossless coder. But of course, also here at the expense of increasing the maximum error, because worst case, we could reconstruct at one end of the interval where actually the true value is at the other end. So at least by the guaranteed bound on distortion is double the way we've done it here. But it's possible to do the trade-off between these two fidelity or distortion measures. If we look at the rate distortion now, just taking the PSNR, then we see the red is soft decoding with the network, and we see a clear improvement over the blue, which is just a straightforward EPIC L infinity decoding. And also we see that while the HEVC reference here was better than the EPIC performance, then now we're clearly better than both of these, and all of them are better than the mu coding. And these are two examples. We also did on this evaluation set, and we can see by Bundegard differences that we get a 3 dB or improvement in PSNR or almost 45% reduction in Bundegard rates. Whereas this is a clear improvement over we just took EPIC, or if we would do, of course, it's better than to do the former SDNet decoding of near lossless. There's another version than it here, which does improve performance, is better than HEVC, but still trailing to this. And then we have mu at the right. So maybe if I should conclude here. and maybe expand a bit on this. So I'm going to say we've been exploring the trade-off between 3 key parameters in image compression: rate, distortion, and time efficiency. So one of the goals was to, of course, have good rate distortion performance, but also keeping the time efficiency or the complexity low, at least on the, definitely on the encoder side. Then, of course, we could do lossless coding, and then, as always, we could compromise by going into the near lossless domain and get higher compressibility, so moving into lossy coding. And then I think we could say here that by this post-processing or the deep decoding reconstruction, we can actually move this, push this near lossless technique into larger distortion. Usually it's fairly limited. Fairly quickly as you increase the step size, you get poor PSNR performance, but this can be alleviated by the soft decoding. And that's what we have in this bullet, that the deep learning can attenuate the errors, reduce it, and then, which we didn't do so much here, but you could also proceed and more flexibly have a trade-off between the 2-norm PSNR distortion and the inf-norm max distortion. And at the end, I would say we have a fairly simple encoder. It can probably be further simplified. And then we presented possible trade-off on the decoder side for flexible decoding. And I also think it could be interesting with these light field images that maybe you don't need to decode the whole data set, or maybe you don't need to decode decode it all at once, but can do it stepwise, and thereby that you could actually allow more complexity on the decoder side, and sort of leave it to the decoder to decide this complexity. Okay, thank you.
Yep.
Thank you.
Thank you.
Thank you. Thank you very much, Soren. Thank you. Can we proceed with Xinjing? I'll introduce properly now. Xinjing received a master degree in Communication and Information System and a PhD degree in Information and Communication Engineering, both from Huazhong University of Science and Technology, Wuhan, China, in 2002 and 2005, respectively. From 2006 to 2008, she was a postdoctoral fellow with the Chinese University of Hong Kong. And from 2008 to 2012, she was a visiting lecturer with Waseda University, Fukuoka, Japan. Since March 2012, she has been with Shenzhen International Graduate School, Tsinghua University, China, where she's currently a professor. Her current research interests include computational photography and light field processing. She has published over 170 conference and journal papers. She's a IEEE senior member and member of SPI and ACM. She's a distinguished professor of Peng Chang Scholar, and she serves as TPC member in IEEE Visual Signal Processing and Communications Technical Committee, associate editor of IEEE Transactions and Broadcasting, and she's the group co-chair of Lens Light Video Coding and ISO IAC WG4. She received the gold medal of International Exhibition of Geneva in 2021, second prize of National Science and Technology Progress Award in 2016, and the first prize of Guangdong Science and Technology Award in 2015, and the ISO CC Best Paper Award in 2010. Thank you again, Xinjing. Please, the screen is yours. Thank you.
Yeah, okay, thank you. Thank you very much for your introduction. Good morning, good afternoon, good evening, everyone. I'm Xinjing from Shenzhen International Graduate School of Tsinghua University in China. Thank you very much for your invitation to give the presentation here. Today, I wish to share with you some of our understanding for the Planoptic image compression, and especially for the end-to-end Planoptic image compression. Actually, why we select or we start to do the compression. Actually, if you look at my research interests, we mainly research on the Planoptic imaging to design the imaging devices. Well, based on our design, we find the something different and the response on the sensor. So using that may also benefit our compression. So that is why we further expand our research to the Planoptic image compression. Well, for the end-to-end solution, actually we just started, I think, for 3 years. Since before it, we mainly used a hybrid coding architecture to compress, or we designed several coding tools that also are presented in WG4 of ISO. So here this work mainly comes from our paper that we published in ICASP this year. Well, we wish that to share with you some of our understanding of Planoptic image to see how we can further improve the compression efficiency. So I'd like to start from the imaging architecture.
Sorry, Jinjin, I think we only see your first slide.
Yes, yes,
okay.
I will continue.
Okay, yeah.
Okay, so I'll first start from the imaging architecture. Actually, you know that the Planoptic imaging compared to the traditional camera is the biggest difference is that it can record the direction of the light. Well, this is the traditional camera that they only convert the rays and to record the integrated intensity on the sensor. So that is why the 3D objects will lose their directional information of each ray. So the 3D objects will become to the 2D plane image on the sensor. Well, the Planoptic imaging is try to fast decoupling the directional information in the light rays and record the direction of each ray and also finally to reconstruct the ray directions. So that is was the major target, I think, of the Planoptic imaging. Well, to realize this, actually, it has generally two steps. First, for acquisition, that needs to record the ray directions, and then using the computational sensing or with a computational reconstruction, that will reconstruct the ray directions. So using this, we can realize that just using one single Planoptic image, we can realize the viewpoint changing, 3D reconstruction, and the refocusing, etc. So these results actually is captured by this Planoptic camera, and this camera is also developed by us. And this is also used in MPEG as one of the acquisition device for the Planoptic video. Okay. So based on this, actually, it shows kind of application possibility or the application potentials in such kind of defect inspection, 3D reconstruction, or VR or AR applications, or the integral displaying, or the visual odometry. Well, for these two, actually, we also designed the systems using such kind of Planoptic cameras. Yeah, this system is also designed by us for the defect inspection. And also we use that for the SLAM, so that the visual guiding for all those robots. Okay, so for these kind of application, this also shows the requirement for compressing the data from that. Well, for the Planoptic images, that are captured by those cameras, we wish to further go a bit deeper, since actually there are two types of the acquisition device. like Planatic 1.0 and 2.0. 1.0, the difference is they put the microlens array at the image plane of the main lens. So it can be regarded as each pixel on the sensor try to record the one direction of the light ray. Well, each micro lens record the information of one object point, something like that. Well, this also shows the existing devices. Well, the other type, the Planatic 2.0, that is to put the micro lens array behind the image plane of the main lens or in front of the image plane of the main lens, using this to generate kind of the re-imaging, or we call the relay imaging architecture. So these micro lens will work like several virtual small cameras to re-image the image at the main lens image plane, and then to generate the image on the sensor. So actually these two different architectures, well, the 2.0 shows better performance compared with 1.0 in the spatial and in the trade-off between the spatial and angular resolution. Well, because of these two different architectures, actually you can find that the image itself, the distribution of the intensity in it are quite different. If we capture the same scene using the Planatic 1.0 camera and the Plano 2.0 camera, you will see the two images are quite different. If you enlarge the same portion or the same position of the area, magnify it, and to see that actually Planatic 1.0, they have so many tiny micro lens, micro images. Well, inside each micro image, there's kind of gradually changing intensity. So, well, those each pixel, generally we say it corresponds to some angular information. Well, in the 2.0, you will find that the micro image is much bigger since they works like the virtual camera. So each micro image is much bigger than that in the 1.0. And also you will see the image in it looks like to watch the object from different angles. So you will find those detailed texture correlations among the micro images. Well, in each micro image, it has some, also have the very detailed textures in it. And also they have some kind of correlation among those micro images, but this kind of transformed creations. So based on this observation, actually we find that if compared to the existing lenslet video coding techniques, that's based on the hybrid architecture. Since generally they have, we directly code those the Planatic image using some intra-coding tool, or we to render it to be the multi-view to be kind of pseudo video and use the inter-prediction tools, or just use some multi-view coding tools to encode them. Actually, all of them shows kind of limited prediction areas or the prediction correlations that can be exploited in such kind of the lenslet video or in such kind of lenslet image. Okay. Well, if we do that using the end-to-end architecture or using the convolutional kernel to extract a feature from it, it may be possible to have larger receptive field to exploit those kind of the long distance correlation in such kind of lenslet structure. So this is why we start to focus on the end-to-end architecture to see whether we can use that. For the first step, we start work on it using the Planatic 1.0 image. So we analyze the image architecture. Like this is the typical image that's captured by the Litro Illum camera. And you can see that first, these micro images are arranged in hexagonal grid. That is because of fully used sensor. But such kind of architecture makes the textures in this image becomes kind of quite different from the regular image. So if you just put it directly into those end-to-end image compression network, it will show very low efficiency in directly compressing it, since the correlations are changes a lot. So we first do some kind of we call it a reshaping process, pre-process, to make this micro image to be aligned to the rectangular grid. Using that, it will to make such kind of correlation to be the shows kind of regular to show some kind of periodical the appearance. Okay, so using that, it will benefit the network. Okay, and then further magnify this architecture, magnify this reshaped image. You can find that for this one micro image, actually in it, the pixels corresponds to the angular information of the rays. So actually we need some kind of angular feature extractor. Well, for the corresponding or the collocated pixel positions in the different micro images, generally they correspond to the different object point, well, at the same angular direction. So we need some spatial feature extractor, okay, to extract a feature from it. And also, if the in the scene, the objects are distributed in the whole scene, so some of the object point perhaps may not be at the focal plane of the main lens, so that its rays may go to the several pixels under different micro lenses. So that results in the different micro lens, they may have the information from the same object point. So that means we need also the angular, the feature and the spatial feature should have some interaction to fully exploit such kind of correlation in the data. So that is why we propose such kind of network. We call it the spatial angular decorrelated network. And using this spatial angular interaction block, feature fusion, and also using the attention network as the backbone to fully exploit its correlation. Well, if you look inside the major contribution comes from this part, that we use the one pass as the spatial correlation extractor. This part is angular feature extractor, and this pass goes through for the spatial feature extraction, and also these two, the spatial and angular, are concatenated to make them can interact with each other to further extract the feature in these two dimensions. Then using this, we can compress it to both to decorrelate in both the spatial and angular dimension. And we tested, or we trained this network on our the data set that also built by ourselves. This is called the PNet. This is the data set consisting of 8,700 these density images, and in it more than 7,000 images are captured by the Planatic 1.0 cameras using the LITRO Illum, while others from the 2.0 images. And also the depth map also included in this data set. And these data sets can cover around 180 categories of the natural objects or natural things. Well, we use the WordNet to do some kind of categorization, like the ImageNet, how ImageNet do. So this can show this data set, the coverage on it. Then using, then for training, we first convert, or we first do the pre-processing for each input raw image using the MATLAB toolbox to do the pre-processing and get the rectified planatic image, and then do the reshaping to align them to the rectangular grid. And then for training, we randomly select 1,000 images from our data sets and pick out the patches, this size of the patches for training, and then select 5 lambda values. And for testing, we test on 12 EPFL 1.0 images. And we compared with 6 methods. This one is the image, the intra prediction on the using the hybrid architecture. Well, they used the Gaussian regression to do the prediction. Well, these 3 are using the intercoding tools in HEVC or VVC. Well, these 2 just to generate the pseudo video by reordering the subaperture images. This one is to do the multi-view prediction, well, just to compress some key SAI and then use the view synthesis to generate the other SAIs. And these 2 are the end-to-end image coding networks. And this one is also entered the CVPR image coding, end-to-end image coding competition, and also get some very good results there. And we compare the compressed or the reconstructed the lenslet image, the quality of the lenslet image. So for each one, we kind of solution, we try to make the comparison in the same domain to show the fair comparison. Okay, so this is the results. You can see that our end-to-end network is the highest one compared with other approaches, and also much better than the end-to-end networks, end-to-end image coding networks. And we also compare the API consistency to see that also ours at the lower or comparable bitrate, its API quality is also much higher. And if visually look at the reconstructed image, you can also see that the textures in it is quite close to the original image and also better than others. Okay, so it shows the good performance of this network. So we wish to extend it to 2.0, and we tested on the 2.0 image. Well, best thing happened, that's 2.0 performance is 1 point, it's just here, okay, much lower than that on 1.0. So it means quite the differences in these 2 types of images. And we further analyze that's the 2.0. That is what we showed here, this long distance correlation in the image and also very complex texture inside each micro image may cause the difference in such kind of compression inefficiency or efficiency, such kind of difference in the compression efficiency. So actually new solutions or new end-to-end networks need to be designed for 2.0 also. This is also what we wish to do in the future. And also we wish to do those things for the videos. This is what we provided for Impact Planatic 1.0 videos. And also we provided that for the 2.0 videos. So we wish to design for that. And also the other universities, Nagoya and Inria also provided 2.0 videos there. So we will also further to extend our research on this. Okay, so this is the end of my presentation, and thank you very much for my members helped me to prepare these slides. Thank you, and welcome for questions. Thank you.
Thank you, Jinjin, for the very interesting talk. Okay, I think we can start the Q&A session. So we had 3 very interesting talks. And yeah, feel free to ask questions. You can just open your mic and
maybe I can break the ice just about the last presentation. Thanks, Xin, for the very nice talk. So these data sets that you created are publicly available? I mean, people can download and use them, or?
Yes, yes, it is public available.
okay.
And we, oh, sorry, okay,
That was also my
will,
question too.
Yeah, yeah, we can provide it, and this is also public available.
Okay, thank you.
So maybe I can ask a question. Hi, everybody. So, you know, a few years ago, there was a lot of hype on these light fields, especially with LITO. You know, the LITO cameras were very popular. And we had the idea that in 2 or 3 years, we would all be taking pictures with light fields. And the situation changed a little bit. We still use a lot of content from LITO Illum, for example. But, you know, LITO does not exist anymore. So in your opinion, and I'm relating to the 3 speakers, what is the real situation in terms of market deployment of light field pictures? What is the real situation? What are the most popular cameras in these days? Where is it happening? Because there is the sensation sometimes that the hype is less than 3 years ago. And it's a very nice research topic, but we are not seeing, for example, the lenslet type of light fields really exploding in the market. So what is your impression?
I can start. Okay, thanks for it's actually a good point. I think this question was raised more than 3 years ago in another workshop on light fields from Banjo, I think.
I'm old, Giuseppe. You know that I'm an old guy. I've been here for 30
No, but
years.
it's interesting because the question is still there, right? I mean, I don't have a good answer to this. I agree with you. I mean, we worked on Lancelot. It's a kind of, you know, my student, when he started to work, he found this data set, he found this kind of data. He said, okay, let's start working on this. Indeed, the computational photography kind of market nowadays doesn't seem to go really in that kind of format. I mentioned other things that seems, in my opinion, but you know, I cannot predict future. But the nerves stuff seems more like to me more in the long term possible direction. So I think that indeed, for the reasons why this didn't really become popular as a commercial product, maybe it's due, you know, to the format of the camera, to the fact that it didn't have a proper market. Maybe that, you know, the other thing is that the refocusing, the change of point of view nowadays, you can do with a single picture, with a single, you know, you have techniques in computer vision that estimate the depth for a single image, and they work extremely well. You can refocus using, again, a single image and generative models. So somehow the question is whether we need the physical hardware. I mean, to which extent nowadays, you know, the balance is between the physical hardware investment, the lenses, the cameras, and on the other side, the computational power. So this, I think it's probably one trend, at least in computational photography, what you can see in the phones, for example. Yeah.
Thank you, Giuseppe.
You're welcome.
Soren, Xin.
Yeah, perhaps I wish to add some information for it. In WG4, we did a market survey, and for the Planatic imaging of Planatic cameras, and also for its possible applications in displaying and the other areas. Now we have summarized that in the output document of WG4. I think the number is N116, I guess. I can confirm it further. We find first several types of Planatic cameras now still available. Some of them are used in the inspect the detection area because of its advantage in such kind of short distance 3D imaging capability. And also another branch goes to the light field microscopy or the medical use area, since also because of its 3D or fast 3D imaging capability. And for its displaying, there are several types of light field displayer, like the integral displayer or some kind of converting them to the phase space and to display light field, or convert them to multi-view, those kind. There are also several different types of the displayers. Well, for the input data, we think this kind of Planatic image, or we call it the lenslet structure image, that it can support all of these types of displaying techniques. Since from this lenslet structure, you can rendering multi-view, you can use it to calculate the face information. Also, you can do that for some kind of refocusing to generate that different layer, that information that can be used for some kind of layer display. So that is why we established that kind of, we call it the lenslet video coding ad hoc group. In it, we think the lenslet data itself is kind of general data format, and then it can support. And for the devices, now it also has kind of devices and applications. Yeah, this is current our investigation, and we shows kind of the market needs of it. So we also wish that if more companies or more universities have such kind of things can join and also provide more information here.
Thank you.
Yeah, I could also give a short comment. I think one distinction would be if you sort of ask this from an academic point of view or for JPEG standardization. So I think from the academic point of view, I think, I mean, it's about having multiple images and the correlations you have there. And there I still think you could also say the old Litro can have some interest. Maybe they should not be like, maybe not just have one test set, but use it in a broader test set. And of course, part of the difference is if you have other multi-camera systems, is this some would formulate it in terms of the baseline, how close the cameras are, and of course the Litro are very close, which gives some advantages. So maybe some like use them in a more diverse setting where you have other base together with other data sets, so you get something that's more robust. From the JPEG point of view, I guess I don't really would have a clear answer, but I mean that would sort of also be policy of JPEG. I mean, probably we should not design a standard which has very good performance on the Litro camera, but I would sort of see it as an open question what data set we should benchmark coming standards on.
Thank you, Soren.
Okay, can I ask a question? It's Eduardo from Brazil. It's for the two presenters. We have here the learning-based methods, okay? But for learning-based methods, we did good training set and diverse training sets. But we have a problem because we do not have that many light field data sets. I think the three of you have used lenslet light fields. And how do you envision with this sort of lack of a diverse data sets for light fields, the future of learning-based light field compression?
Yeah, that's indeed a big issue for all learning-based methods. I think it's you know, the same problem, whatever learning-based task you do. And you know, one of the issues, if you want, it's also related to the quality of quality assessment for images. You know, you can find always a way to optimize your method to give good performance in the paper for that data set if you want. So this is a big, very big issue. Definitely having more variety in the data would be good. Having cross data set validation would be, should be like standard way to validate the results. Doing some data augmentation. So we tried doing data augmentation for example, for the lossless work I presented by changing, you know, doing some kind of gamma transform on the pixel intensities. You know, I think this is a very big question in general for the learning-based methods. So definitely having more data, it's good. You know, the advantage here is that it's compared to other tasks in computer vision, compression is not supervised. So we don't need the labels, we don't need human labels there, right? So this is an advantage, but indeed, yeah, we have this this issue. So yeah, I think it's as Soren also said, we need to increase the data sets and have more diversity.
Can I add one more question that's related with the question of Eduardo?
Sure.
Can I? Hello, I'm Caroline. Caroline Conte from Portugal. I just want to add a question. What are your feeling, you people that are working on light field coding, using deep learning, what are your feeling of using videos with camera movement for training? Do you think it's enough? It could help in this case, because we see many authors using for rendering.
Yeah, that's an interesting yeah, it's actually, I think people have done this for, well, I saw some work on recent stuff with nerves and so on. They do some short video and they reconstruct 3D of the scene. So, you know, at the end, if you can reconstruct the depth and the geometry, you have the work done, right? I mean, you can have the representation of the scene and reconstruct the light field. So indeed, it could be an interesting way. I'm not aware of explicit work doing this for compression, but I think it could be interesting to investigate. Yeah.
Thank you.
Okay.
So if I may, maybe as a follow-up question, it's a bit related with, it's related to the question that Fernando asked before. But before doing that, I would like to thank all the speakers for their very interesting presentation. So it was very insightful. So, but I would like to follow up on the questions, on the question of Fernando, because that started basically from the acquisition side. So the question is, and it was partially touched upon also by Chinyi already. So whether we shouldn't more look from the display side and basically from the receiver side, because in many applications, but like it's also the case for regular video and image transmission, basically you want to have a decoder that is sufficiently, let's say, lightweight, so that you, particularly in broadcast type of applications, so that you don't spend too much processing power into the reconstruction. And for light field is typically one of the problems, particularly when you want to synthesize them up front, so that there is a lot of processing power necessary to generate them. So the question is, if you look at it from the display side, and we take now into account all the solutions you have been proposing, and I'm looking now to all the speakers here, would those solutions work well, given the type of displays that are around right now, knowing also that due to the fact that you have to transmit a large amount of information, that you typically, okay, we'll have to support particular viewing angles and not necessarily, especially when you look to really high-end displays, and not necessarily have to reconstruct the full actually reconstruct all the views, but only a particular, let's say, range of viewing angles in order to support the user who's in front of the screen. So with the solutions that have been proposed today, would they actually support this kind of scenario?
I guess it's an easy answer for my approach, okay, which was to have a very easy encoder and then allowing more complexity for the decoder. So that's the opposite direction.
Yes, but so in what sense would that be scalable? So is that
okay? Yeah. I mean, it is scalable on the decoder side. Yeah.
So you could actually send particularly only one view and then, or a few views, and based on the intermediate views for a subset.
I think more work should be done, but I mean, so it's. I would not say what we're presenting is like a finished solution, but more sort of research work on using the deep learning. But true.
So looking to Xining or Giuseppe.
From my point of view, what we did is to compress all the information and then transmit. Since input is the lenslet data, right? That is mainly because currently there is not a very mature device that to say it can show light field good. I'm not, perhaps others have different understanding, but this is currently what we found. Like if the multi-view display, I think this is may not, it also still shows some kind of difficulty for very those natural videos or natural scenes, right? To generate very continuous and also to make everybody can watch it with very high or very good immersive feeling. Well, if for those kind of holographic solution, this is more difficult to compress the face information than the image. Well, for the integral displaying, that may be the closest one to the lenslet capturing, but now its quality is still need to be improved. So that is why we think if the compression to be used or can be used for all of these possible types of display, we have to compress all of them, and if for like just now mentioned, for actual Planatic 2.0 image, the raw image, the resolution is not as that high as the 1.0, since they have a better trade-off. So it's still possible to compress that, since the 2D, if 8K 2D image can already be transmitted, right? So for 2.0, lenslet it still has the bandwidth to transmit it. So that is our current.
That's why, yes, that's why I said, okay, let us look to the display side, because still the variety of types of sensors you can use at the acquisition side is still too large to say, now we're going to have one standard and that's going to be a solution solving all, as you also stressed actually during your presentation. But the reason why I said, okay, assume that there is only one viewer is also because then in that way you can actually limit the viewing angle range that you need to support. And so you might also think in that context at head-mounted displays. And let us forget for a moment that we have a streaming solution that can very fast stream all the different views separately and so, but assume that you want to send some kind of compressed format that immediately supports let's say, a relatively limited range of viewing angles, such that you immediately can compensate, for example, also for head motion and so on, that you have immediately readily available, actually, or fast available, actually the content you need to support that as well. So that's why I was asking that question.
Yes, actually, there is some kind of interaction between that. This will be better.
Yes.
Yeah, I think, I mean, what you were mentioning was actually what I had in mind about the, I mean, the baseline, of course, is much more reduced than when you look at 360 video, right? But there you have a lot of work done to, predict the saliency, where you're going to look, make this kind of navigation. So this one, in this case, it's more reduced, the margin that you can have. But I think that, you have, so like the method we did for lossless, is based on hierarchical view synthesis. So you can, avoid having all the views decoded. You can select somehow which are key views that can give you, can move you towards the views to present. Now that vector, you can do this real time. This is a more complicated story, but I think it's an additional factor that you can have. At the end, if you want to obtain this kind of random access on the views, I think having flexible prediction structures where you can predict from different key views, it's quite probably, yeah, it's quite important.
Okay, thank you. I have another question, unless there are other questions popping up, but not immediately, I see. So let me ask another question. And so we didn't stress this really at the beginning of this workshop, but so the JPEG committee has been working already a while on solutions that are based on deep learning for encoding multimedia content. So we have, for example, currently the JPEG AI activity that is focused on learning-based solutions for still images. And there is secondly also another activity which is focusing on point clouds, where we have currently also a call currently open that is focused on using learning-based solutions for point cloud. And actually both activities, they have actually as philosophy, not only to support purely the compression of this type of data for the purpose of visualization. So where you actually generate latent representation, you compress the latent representation, and then you have a decoder, again, learning-based, that is actually reconstructing the views. But that is also meant to be usable for, let's say, functional analysis of the content. So in the terms of point clouds, you can think about using that for actually depth estimation or whatever. So all kinds of applications, and the same in the context of still images. And so the question I have to you, Tree, is actually, okay, so we also play with the same idea, of course, for light field. And so the question to you is whether you think this is a good strategy based on the experience you have using these learning-based solutions for light fields. And so the question first is, okay, whether you think it's feasible, of course, also whether it's a good idea to think in this direction as well for this.
Well, I think it's obvious when you have the learning-based approach that you consider also providing other features than just the compression. I think that's quite obvious. For the other part and for light fields, I guess, I mean, sort of yes, I mean, it's part of it would be in the training, but sort of beyond this very general response, I'm not sure I can sort of.
Well, one thing that I believe it's interesting, and it's different, the light fields compared to images and but also point clouds, is the fact that in light fields you have multiple choices for the representation you want to use, right? So you showed, for example, Soren, that you could have APIs, but you can have sub-aperture images and so on. I guess, for depending on the task that you're gonna use, probably some input representation can be more adapt. Like APIs seems to be very good to detect the structure of in the 3D space and so on, right? So this is something more than you don't have in 2D images. You don't have this choice, right? So I think this is also something to be honest, I'm not much aware of the works on analysis for light field content, you know, for in computer vision and so on. But it's something that I wonder if should be considered. And I guess that this depends a lot on the task at the end of the day. So it's maybe there is some question there to investigate.
Thank you. Xinjing?
I think they have already expressed some of my thinking.
Okay.
Okay, Eduardo speaking.
Yes.
Again, as a follow-up question from Peter's one, do you think we, in terms of data sets, again, do you think we have enough data sets right now to start such an activity or not? And what would we need? Do we need larger baseline data sets? Do we need more or less data sets? What the three of you think about that?
Maybe also a follow-up question, which is related to Eduardo's question. So we have all seen like different compression methods, also like view synthesis techniques that you described. But usually these kind of things are always evaluated on lenslets or like narrow baselines. So do you see that, do you think that they are like generalizable to like wider baseline, or if there is a problem, how you should be able to solve it?
Yeah, I don't think we should rely on the narrow baseline and then assume that we generalize from there. I mean, of course, I think we should definitely have something with a larger baseline if we want the solution to be robust to that. I think that's quite obvious.
Yeah, I think that it requires some change. I can tell you that I don't know if we probably tried some small things, but you know, already view synthesis is much more complicated, and you know, the kind of tools you use might also be different. I mean, it's not obvious to extend and say that it's the same kind of task. So it would be definitely interesting to work also on the more wider baseline. For the task, for the question of Eduardo, I think for me, for example, it would be very important to understand which kind of task we consider, right? Because, for example, I think, I mean, and there I'm very ignorant, but before Xinjing was saying that there are applications in medicine, applications in for controls of industry. So I mean, this kind of application are quite interesting, and I'm not sure that there is a lot of information. I mean, personally, I'm not really aware about this kind of application. So I guess that if you want to work towards a task-oriented compression there, you first need to be aware of the task. You know, it's not the usual thing you do in images. In images, you take the benchmarks are kind of standardized, right? You take segmentation and you have data sets for that and so on. For light field, we don't have this. It seems to be more custom and more specific application. So this, I think, it's also a limitation for research, at least for academic research. There.
Yes, and Giuseppe, and talking about, suppose, for example, that we are not concerned about the tasks right now, but we are only concerned about compression. Do you think the status of the data sets that we have now is enough for pursuing such a standardization activity? And if not, what do you think do we need in terms of data sets?
Yeah, I mean, definitely, as I said before, the data is key when you do the learning-based methods. I mean, anticipating the diversity that you can have at test time, right? It's always difficult to you make what is called an inductive bias, right? When you learn, you make some kind of hypothesis, and this condition what the network is learning. This is one of the assumptions in machine learning. Now, I think that definitely what we can do right now, it's mainly for the case of Lancelet, at least for my work. Already extending this to wider baseline camera arrays probably is an important next step. In terms of content, we have, I mean, it's good to know that now there is bigger data sets like Xinjin mentioned. I think definitely it would be good to increase both for the training, but also for testing, you know, because as I said, this is a greatest risk every time you see papers on learning-based methods. It's not difficult to optimize your, you know, to get the good results at the end for that data set. So I think that again, having more variety of it's not just the quantity; it's really the diversity that you have that matters. So this is an open problem.
Yes, and also because of the differences between the 1.0 and 2.0 image, we need to increase the data amount for the 2.0 Lancelet image, since its distribution is quite different. I think that will greatly benefit the application. I think now the 2.0 tends to be the has higher potential for a wider application area. So that will be better. Yeah.
By the way, it was just coming to my mind that, you know, another issue that is always fundamental, and I think we still didn't mention, is the quality assessment. And in fact, also in JPEG, we have an activity to develop quality assessment, not only subjective protocols, but only objective metrics. And we intend to do it starting with the subjective assessment protocols in a collaborative way. So we are issuing a call soon. And as we all know, you know, this quality assessment, the subjective and objective, is really a broader and a very important element for the good development of the compression solutions. So if you are interested, guys, you know, we are also working on that part, and we welcome very much your contributions on the quality assessment part.
Yeah, very good idea from Manuel. I'll send them the call for contributions.
So as a follow-up, because that is the next question. Okay, what is your experience currently in the tests that you have been doing and the developments? So in terms of quality assessment methodologies, both on the subjective testing as on the objective testing part. So what are there typical shortcomings you're observing with respect to the technologies that you have been investigating or designing currently that really make it very difficult to do really an efficient or an adequate quality testing? So can you comment on this?
I'd like to share with you some of our thinking. That's the quality assessment problem is a big problem actually in the light field compression. We try to multi-view the subjective quality assessment using the multi-view render from the Lancelet, and then design a kind of order to watch it. But actually, this is still not a kind of good way to watch the light field, right? So this kind of the route from which view to which one, this is I think this is too subjective. I think without any fully support from the device or from those. And also try to watch that using kind of head-mounted devices to see the 3D feeling. But that is not enough for like the general 2D TV that or those devices we can watch it together, right? So that is still also limited. And the one problem and exists is also for the Planatic 2.0 image. If it's rendered to the multi-view, it cannot render back, or it cannot be converted back to the lenslet. So that is why generally we directly compress the lenslet image for Planatic 2.0 data. And that will be also the data amount will be much smaller than to the multi-view. So as we do the compression, we will directly do that. So we found perhaps it still works directly, just compare the PSNR together with bitrate for lenslet image itself. That is no matter how to generate the multi-view things, especially for 2.0 lenslet. If you generate to multi-view, there are different types of methods that will also influence the quality. So this is our current solution that just directly compare the quality for the lenslet image for the 2.0. But for 1.0, since the conversion from lenslet to multi-view is lossless, so this can use multi-view to do the quality evaluation. But how to watch those multi-views is still a problem. So we currently do not have a good solution for that.
Yeah, I didn't work on quality assessment for light fields. I've been working more maybe on point clouds and traditional images, but I think that as Xinjun was saying, one of the question when you talk about quality of experience is which kind of experience we talk about here, right? Because the point of having light fields is that you want to watch somehow, you want to have something more than just the conventional images, right? So I made the example of changing the viewpoint or refocusing. So this implies some kind of interaction, and this complicates things in QoE because you are not used to evaluate tasks where the viewers can decide what to watch. This was the same problem for point clouds. There are solutions to this. I don't know if they are the good ones, but this is one aspect. There are, when you look at the objective metrics and you think about many works that have been done for conventional quality assessment of 2D images, there've been a lot of work on the perception, on visibility and masking. So when you try to translate this to light fields, you say, okay, what is masking in the geometry in the light field, or right? So this is another kind of, another question that I may be naive because probably people maybe worked on that. I'm not really aware of the state of the art there, but I think it's a general concern that I have for immersive content and quality of experience. There is this aspect of it's not just conventional traditional viewing as we are used to in the subjective experiments where you show to every observer the same thing on the 2D display. I mean, here we expect. The full goal to get these technologies to provide something more to users, right? So I think this is one of the questions to consider.
Yeah, I would maybe rather go back to the question before about the data set, but data sets, but of course it's related. It's part of the quality assessment. So if we go back to classic video, then we could characterize in terms of spatial and temporal index. And I've not really say that I've ever sort of really been part of defining a test set or benchmark, but of course over the year using what was there, what was accepted in the community, but it would seem to me that that could be one of the sort of approaches towards those evaluating the existing sets and going forward. But I guess could again use for spatial and temporal index, but probably more. And then we've been talking about baseline, but I think just taking baseline is probably too simple, because that's like a technical parameter. So, but I don't know if we could come up with a sort of relevance visual measure or perceptual measure that would capture this.
Maybe I can ask a very pragmatic question, because we are facing this problem in other activities. So you learning-based guys, are you PyTorch or TensorFlow? Because one of the issues is that depending on where you are working, it's quite difficult to collaborate, because if you are one side of the river or on the other side. So, but for example, in MPEG, for at least for point clouds, they decided to adopt PyTorch. Do you have any opinion on these PyTorch or TensorFlow?
I think my person, I mean, this is what my students tell me, because myself I'm not really, but it seems PyTorch becomes more like the standard way, at least in computer vision. TensorFlow, it was quite popular for compression, because the guys of Google, they did their library,
Yeah.
and now there is a version in PyTorch from Interdigital, I think. So I think that now the new students, I tell them, you should be able to understand both, because you can find tools and code in both. But I think that it's better to do your own code in PyTorch. Probably it's more future-proof. Yeah.
You agree, Shin?
Yeah, my students like to use PyTorch.
It seems it's more popular in these days, clearly.
I'm quickly making a poll for this group. I would like to see the.
Sometimes it's a problem. I think that, for example, in the point cloud exercise, we will have to have some discussions, because I think that some of the proponents are one side or the other side, and so we have to take a decision for the reference software. And so this is really an issue.
No, I didn't know there was this feature, and that's cool. I should learn to use this.
Well, good move, Peter. You were quick. I think you are practicing with your students, I guess.
No. This is the first time I'm using this, actually.
Yeah, really.
No, the user interface is very simple, I must say. I don't know whether you can see the result, because I see the.
You can, I hope you can see the results.
I can see the result, yes.
No,
So
we cannot see.
Currently 14 votes, and 80% says PyTorch and 20% TensorFlow. A quick balance in the group here. Yes. Yep. You stay there. 75%, 25% is balance currently. Okay, thank you.
We are two minutes away from our from 15 UTC. Any other questions for our speakers?
I think no. There was one hand raised by Caroline, but I think she gave up.
Oh, I do not see any hands raised by now.
She's not there anymore.
Oh, okay. Okay. So if everyone is happy, we would like to thank you very, very much, Soren, Giuseppe, Shinjin, for. Oh, sorry.
Thank you. For
sorry, Lisa. Okay, something related to Google. Okay, I would like to thank you very, very much for being here today with us and sharing your experience and your excellent presentations. And for our talk, the talk is the best part of the workshop ever. Thank you very much.
Thank you.
Thank you. Bye.
Thank you.
For all that come to attend our workshop. Thank you very much.
Bye-bye.
Thank you.
Bye.
Bye-bye. Bye, everybody.
Bye.
Thank you.
Bye-bye. Bye-bye.
Okay, I believe we will see each other again tomorrow. At,
Yes,
group
7 a.m. my time.
Yes.
No, it was late for changing. I believe it was 11 p.m. for her now. Or no?
Okay. Yes, it was quite late.
Yeah. Yeah.
Okay, good.
Okay.
So
Thank
see you
you.
tomorrow.
Bye bye. Thank you.
Bye.
Bye.
Bye bye everyone. That's you and Paul. Bye bye.